So here we are to talk about Thevenin's theorem. And this is one of the most useful theorems. I should say, understanding the significance and the meaning of this theorem is so fundamental to electronics and circuit analysis. And the reason is that when you design a circuit or system, you usually don't design it where it just lives in the world and never connects to anything else. Most of the time, you design a circuit or some system, and you intend on connecting it to maybe one other device or component or entire other system, or it could be connected to, by its application, connected to a variety of devices or other applications. For example, let's say you create a motor controller circuit. Now, when you create a motor controller, you're an engineer working in a lab, and you create an electronic circuit that can control a motor. You don't know exactly what motor somebody is going to connect to your motor controller circuit. And let's say you design it, it's a 24-volt DC motor controller or something like that. Well, you don't know exactly which motor somebody's going to connect to it. So the interconnection of components and circuits is fundamental to electronics design. Let's say you create an audio amplifier that can connect to a speaker. You don't know exactly what kind of speaker somebody's going to connect to your audio amplifier, and so it'll behave differently depending on what you connect to it. Thevenin's theorem, what it allows you to do is to take a circuit, a system, and then reduce it down to let's over here on the left-hand side, if you have a linear circuit, no matter how many resistors or voltage sources or current sources are in it, you connect it to some load, RL. That load is going to see a specific, this linear circuit really looks like the circuit on the right-hand side. The load, if it was a motor or if it was a speaker, the load itself, what it, quote, sees, it doesn't really know anything about the rest of the circuit that's inside of here, inside of this linear circuit. All it knows is that it looks like, what it looks like, if you were to sort of draw a dashed line here, and everything to the left of this dashed line, what does the load see looking this direction? What the load sees is it just sees there's some source of electric pressure, some voltage source, which, as we'll discuss today, we're going to call Thevenin, in series with some resistance, Thevenin. And that's it. That's what Thevenin's theorem is that you can take any circuit, no matter how complicated it is, as long as it's a linear circuit, and we talked about the definition for linear circuits last week, there is a technique that you can use to reduce it down to a single voltage source in series with a single resistance. Now, why is that useful? Okay, here's the reason it's useful. Circuits are not usually as simple as a single voltage source in series with a single resistor. They're often much more complicated than that. However, the behavior is like to a certain circuit component that you connect to a port of that circuit, like the AB port we're showing here, doesn't really matter how complicated that circuit is. Really, all that load sees is some source of electric pressure, the voltage, Thevenin, driving through some series resistance, Thevenin. And that allows you to then talk about how circuits and components, or circuits and other circuits, behave when they're interconnected. And then you can easily describe and visualize and calculate current and voltage transfer, energy and power transfer, and things like that. Very, very important in designing circuits where there's subsections of one stage driving another stage, driving a third stage. And you want to see how energy transfer is accomplished through each of those subsequent circuit stages. Why deal with the entire complexity of each sub-circuit stage with all the resistors and voltage and current sources within that stage, if instead you can simplify it down to a nice, simple voltage source in series with a resistance? The so-called, as we will use the terminology, we'll call this the Thevenized circuit. That's the circuit after we've so-called Thevenized it, figured out its Thevenin equivalent. Okay, so how do you Thevenize a circuit? That's the subject of our study this week. Take any linear two-terminal circuit and you can replace it by its equivalent circuit of a voltage source V Thevenin in series with a resistor R Thevenin. Okay, and that's how this is Thevenizing a circuit. How do you Thevenize it? What is V Thevenin? Well, V Thevenin is equal to VOC. OC, we've seen that terminology before. That stands for open circuit. It is the open circuit voltage at the terminals. So if you take the load resistor out and you replace it with an open circuit, what is the voltage across those terminals? The open circuit voltage at the port. That's V Thevenin. R Thevenin is the equivalent resistance seen at the terminals with all of the independent sources turned off. All right. Very important that you can only turn off the independent sources. You can't turn off the dependent sources, as we'll discuss in a moment, because they change the current to voltage, current and voltage relationship at the port, which we'll talk about more as we go through. Okay, so R Thevenin is the resistance seen at that port if you turned off all the sources. So in a lab, if you didn't have any dependent sources, everything was independent, and you just took all the voltage sources, disconnected them and replaced them with a short wire, took all the current sources, disconnected them and left it as an open circuit, and then you got your multimeter and you measured the resistance at the port A and B, and you put your probes right there. Whatever resistance you measured at that point is the Thevenin resistance of the circuit. And the load needs to be disconnected as well, right? Because otherwise you're measuring it in parallel with the load. Okay. Now, before we go on any further, I just do want to make this disclaimer. That's usually not a really wise idea to just go ahead and put probes onto a circuit, because oftentimes there are dependent sources, and that doesn't work so well. Okay, so let's jump in and look at an example. We'll lead through. We'll sort of show by demonstration how do you Thevenize a circuit. So here's a circuit with a couple of voltage and current sources, and we want to find the Thevenin equivalent circuit with respect to the terminals A, B. A load resistor is shown with an arrow pointing through it, meaning that that load could change. And the nice thing is that once you've Thevenized a circuit, you can then easily calculate for voltages and currents delivered to the load by varying the load. And we'll find the current for a few different loads of 6, 16, and 36 ohms respectively. So to visualize what we're going to do here, we're going to Thevenize this circuit and thereby figure out what is the Thevenin equivalent here, where this would be R Thevenin, and this is V Thevenin. And we're Thevenizing about the points A, B. That's really all we want to find. Just for completion's sake, we'll talk about the fact that this would still then be connected to a load, RL. But we're Thevenizing the circuit just to the part shown in sort of darker blue. We want to find V Thevenin and R Thevenin. So let's find R Thevenin first. Okay. Doesn't really matter which one of these you find in which order. They're found independently, and then you can, and then you just, then you know the values of each of these. So finding R Thevenin, this is the resistance seen into the port AB with all of the independent sources turned off. Okay, so let's go ahead and redraw the subcircuit. All right, if you wanted to visualize that, that's what this looks like here. It's R Thevenin looking into that port. Okay, what is RL? What is the load resistance C? Let's go ahead and draw that in here. So we're going to short the voltage source, turn that off. Here's the 4 ohm resistor. Here's the 12. Here's the current source where it was. And then here's a 1 ohm resistor, right? And then there is the port AB. And so we're looking for R Thevenin. That's the resistance seen looking into that port. Okay, and R Thevenin here is, well, what do we have? We've got, you know what I like to do when I'm looking at this Thevenin resistance, the resistance seen across this? We've done this earlier in the semester. You just kind of think about what you have to walk through. So if you're like starting at port A, you're going to start walking through port A, walking into port A, and then you're going to walk through that whole path, and you're going to encounter some series combinations. You're going to encounter some parallel combinations, and just write out an expression for it as you go around until you finally get around to port B, and then you've completed through the circuit. So R Thevenin, it looks like it's a 1 ohm. We encounter a 1 ohm resistor. And then we encounter this, which that looks like, if we slide the 4 around to the side, it looks like it's a 4 parallel 12, right? Which is 4 parallel 12, that's 16, no, sorry, that's 48 divided by 16, which is 3 ohms, I think. So this is 4 ohms right here. Okay, so we've just found one part of the Thevenized circuit, R Thevenin, and that is equal to 4 ohms. So we're done with that portion there. All right, now we need to find V Thevenin, which we'll do in purple here. And remember that V Thevenin is equal to VOC, the open circuit voltage. So that's crucial. You want to draw the circuit with without anything connected to it, no load connected there at all. You know what, it looks like I need a little bit more room here, so I'm going to draw this a little bit smaller. So R Thevenin, let's just do this again. This is a 1 plus 4 parallel 12 is equal to 4 ohms. Okay, and now we've got a little bit more room to work with here. So here is the 32 volt source. Now that we're looking for the open circuit voltage, you turn all the independent sources, in fact, all of the sources back on. So here's our 4 ohm and our 12. Oh, whoops, this is the 4, and here's the 12. Then there was the current source here. There's a 2 amp going in here. There's a 1 ohm, and then that is, there's the ports A and B. And we're going to then connect everything there. Okay, so everyone agree with me that the open circuit voltage is the voltage shown at that point. It's VOC. Okay, now VOC is equal to, by definition, V Thevenin. Right, now, do you guys agree with me that, just imagine this, I'm going to go ahead and erase the load right here. We're going to disconnect the load from that upper diagram, V Thevenin there. And do you agree that this would be VOC is the open circuit voltage in that diagram, right? You disconnect it, there's no load. If you disconnect the load, there's no current flowing through our Thevenin, and therefore there's 0 volts drop across our Thevenin. And therefore, it's clear to see that the open circuit voltage across the port AB is the same as the voltage across the source, Thevenin. Right? So that's another way for you to convince yourself that VOC is equal to Thevenin. All right, we'll draw the load back in there now. Okay, so here's RL. All right, now similarly, if the open circuit voltage VOC is shown there, then you know how much current is going through this 1 ohm resistor? By the same analogy, if it's open circuit, there's nowhere for current to flow through that 1 ohm resistor. And so there's 0 amps of current flowing through it, which means there's no voltage drop across it. Right? You can say that there's 0 volts across that resistor. So then what we say is that 1 ohm is this node right here is pulled up to the same voltage, or pulled toward the same voltage as the open circuit voltage, or as the port AB. So that node is Thevenin. Let's go ahead and draw ground on here since we're talking about node voltages now. Now there are a couple of ways you could go here to find Thevenin. It might be fun for us to try it with superposition now that we've done that. My notes actually do this with a nodal analysis approach. So I'm gonna do that for right now, and maybe in a minute we can go and take a look at doing superposition. So let's do nodal at Thevenin at that node. Okay, so we've got 32 volts minus Thevenin over 4. That's through the 4 ohm path, right? Then through the 12 ohm path is going to be a plus 0 minus Thevenin over 12. And then you've got this 2 amp current source going in here, plus 2 amps is all equal to 0. And if you solve that, you'll find that Thevenin, hold on here, Thevenin is equal to 30 volts. All right. Now, could we do that using superposition? Boy, we sure could, couldn't we? What if I just took the snipping tool here and we just crop this out? Do you guys see a way for us to find that Thevenin using superposition? I kind of see it. I see it, and we don't even have to redraw the circuit. Do you see that Thevenin is the voltage across this, right? Across that current source. Now, if you turn off the current source, do you see that it's just a simple voltage divider? It's 32 volts going into that voltage divider in the 4 and a 12. If you turn off the voltage source, that becomes short circuit, and then it's just the 2 amp source driving into a 4 parallel 12 combo. Let me write it down without drawing any subcircuits to maybe model that process of how I'm thinking through it and seeing it, and then we'll draw the subcircuits, and hopefully this helps you to get even better at using superposition, sort of looking at the circuit without redrawing it. Okay, so how I would do this is I'd say that Thevenin is equal to Thevenin from the 32 volt source plus Thevenin due to the 2 amp source. And we can just write down the expressions for those things. All right, so Thevenin, well, Thevenin due to the 32 volt source, as I said, if you turn off the current source, you're going to have an open circuit there, and there's still no current flowing through the 1 ohm resistor, right? So if I cut this here and there's still 0 current flowing through that guy, then all of the current flows through the 4 and the 12, and we do have a voltage divider action, and the voltage across that 12 ohm resistor is Thevenin. So I can actually just do 32 volts times 12 over 4 plus 12. All right. Now let's do, so that's the voltage due to the 32 volt source. Now let's do the current source. All right. So if we're doing the current source, now that's on. There's still no current flowing through the 1 ohm resistor because the port AB is open circuit. And if we short the 32 volt source, all of the current, all of the 2 amp source is going to flow into that node, this node here, which splits between the 4 and the 12. Or in other words, you could say 2 amps flows through a 4 parallel 12 combination. And that's just a simple Ohm's law. You've got 2 amps flowing through a 4 parallel 12 ohm resistor. Okay. So hopefully you're seeing that without having to redraw the circuits. I'll redraw the circuits in just a second. So this is going to then be 32 times 12 over 16 plus 2 amps times the 4 parallel 12. We just said that that's 3 ohms, right? Okay, so this is then 32 volts times 12/16 is 3/4, right? Plus 6 volts, 2 amps times 3 ohms. Okay, 3/4 of 32 is, let's see, 32 divided by 4 is 8, right? So that's going to be 24 volts. 24 volts plus 6 volts, and lo and behold, there's the 30 volts that we got on our slide. Let me close this. We got 30 volts on our slide. Okay, and so we've just found 30 volts by doing superposition instead of doing nodal analysis. And I guess the thing I'm trying to convince you of is that once you're good at superposition and you can kind of see it without having to redraw the circuits, there's less of all that drawing work that you have to do. And you can jump to writing equations that are pretty straightforward. And perhaps easier to do the nodal analysis because you don't have all those pesky, difference in voltage divided by a resistance term, and then you have to clear out the denominators and stuff like that. Sometimes it's easier to do in superposition. Do you guys see it? Do you see what I did? You want to see the subcircuits? All right, so let's take a look at, I'll just do this and I'll try to color code it. So, right, so like V Thevenin due to the 32 volt source. Remember how that was like I said this was voltage divider, right? So when you turn off the other source, you get something like this. Here's the plus 32, here's the 4, here's the 12, and then this is open, and then this is going nowhere, right? So there's no current through this. So what I want you to realize in your mind is that since there's no current through that, the voltage across this is VOC. Both of those things are VOC because there's no current through that 1 ohm resistor. You can basically just get rid of it. You can just short it, whoops, that's not what I wanted to do. Oh, okay, there we go. You can just, short it like this because there's no current flowing through it. All right, you see that? That's the voltage divider term. Now, if we do the other one, let's do that one in, I don't know, red or something. Right, the voltage due to the 2 amp source. Realize when you turn off the other currents of the voltage source, here's your 2 amps. You could draw this like that, but nothing's there. Nothing's going through that. So the voltage across that is that thing there is the so here's the 12 and here's the 4, and then this has been shorted, right? Okay, and so when you redraw it again, which again, I want you to get better and better at doing this in your mind. This is a 4 parallel 12. And then you see that all the current, all that 2 amps flows through there. And then you're just looking at the voltage across that. And that is VOC. Okay, so I spent a little bit of time looking at this. I hope this is useful for you to see further techniques in using superposition. Okay, let's move forward. Now that we've Thevenized that circuit, we can take the Thevenized circuit and then use it to find circuit voltages and currents delivered to the load. So if you want to find IRL, now you have an expression for IRL. How much current is delivered to the load? It's easy to figure out. It's 30 volts. That's V Thevenin over 4 plus RL. Now, if you wanted to write it out, we could actually write it out. This is V Thevenin over R Thevenin plus RL, or 30 volts over 4 plus whatever RL is, right? So if you have that the load resistance is 6 ohms, then you can go and find that the load current is going to be, well, it's 30 volts divided by 4 plus 6, that's 10 ohms total, that's 3 amps, right? For a 6 ohm load, you're going to deliver 3 amps of current into that load. For a 16 ohm load, how much current are you going to develop or deliver to that load? More or less? It's going to be less because the load is lower. It's a smaller load. In other words, the resistance is higher. This is 30 over 4 plus 16, which is 1.5 amps, right? Okay, so you can continue on in that way. We could do it for 26 ohms or whatever the next one is. And we'd find out these, let's just go ahead and do it, I guess. So this is RL equals 26 ohms. Then the current delivered to the load is 30 over 4 plus 26. And that's clearly 1 amp. All right, so as the load is going up, clearly the resistance is getting higher, which means the load is lower. The current is smaller and smaller as well. All right, if you wanted to find voltages, clearly you can just use voltage divider. Now that's something we're going to revisit as we go through. So if you wanted, let's say the voltage delivered to the load, now it's really easy. The voltage delivered to the load is just always going to be V Thevenin times RL over R Thevenin plus RL, like that. You just use a voltage divider equation, and now you can find it for any load resistance. It's pretty straightforward. That also is very important when we're talking about connecting sub-circuits. So just a look ahead. We're going to actually see this in chapter 5. But when you have one sub-circuit like this, a source Vs with a series resistance Rs, and you connect that into, eventually, like let's say this was an amplifier, or let's say it was a microphone, for example. A microphone you connect with a wire and you connect it into a microphone amplifier, right? Well, it turns out that at the input of that microphone amplifier, we're going to see next session, it has an input resistance, Ri. And this is a look ahead. Don't worry about this too much yet, but in these circuits, that amplifier will develop a voltage that is, let's say you had a voltage Vi here. This is going to give you a gain G times Vi, whatever the gain is. So maybe it's like, if it's a gain of 10 times Vi, the gain would be 10 volts per volt. And this would be an output resistance RO or whatever. The point I'm trying to make here is that the voltage delivered, Vi, the voltage delivered to the, let's say this is a microphone and this is an amplifier. the voltage delivered to the input of the amplifier, VI, is not equal to Vs. It's not equal to the source voltage from the microphone itself. It is in fact going to be less than Vs. Why is that? Because there's some current flowing in the entire network now that you've interconnected two subsystems, and you're going to get a voltage drop across RS. And that voltage drop across RS is going to be what reduces the input VI from Vs. So really, if you wanted to find it, you could say VI is equal to Vs minus the drop across RS. Or if you wanted to look at it in terms of voltage divider, now that we've Thevenized that circuit, you can find that VI is just going to always be Vs times Ri over Rs plus Ri. So that's the importance of Thevenizing a circuit. This whole thing right here inside of the microphone very likely is more complicated than a single voltage source in series with a single resistor. In fact, many microphones have a built-in sort of amplifier in them that consists of various transistors or tubes sometimes and things like that to produce the final output signal at the cable. So to be able to Thevenize all the complexity inside of some component, let's say a microphone in this example, down to a single voltage source in series with a single Thevenin resistance allows us to very easily look at the interconnection of those circuits and see how they behave when connected to one another, right? That's my case in point of why Thevenizing circuits is so important. So I know that was a little bit of a look ahead. We're going to see that in chapter 5 as we go into op amps, but I hope that it helps give you some context as to why this is so important to be able to do this.